Good morning. Welcome to Module 10, Introduction to Acoustic Phonetics. In fact, this is the first of the 7 modules to be presented on acoustic phonetics and acoustic physical properties of sound waves, transmission properties of sound waves. In the earlier modules, you must have learnt about the articulatory phonetics, articulatory properties, which are basically production properties, how sounds are produced. The acoustic phonetics, the area of acoustic phonetics actually falls within the domain of phonetics, with not just articulatory and acoustic phonetics, but a third aspect, which is the auditory part. So, a complete description of a speech sound actually must include processes involved in the production, transmission and auditory effect of the sound waves. So, all put together, it is the sum total of articulatory phonetics, what we describe in articulatory phonetics, acoustic phonetics and auditory phonetics. Acoustic phonetics therefore is integrated with the what comes before and after. The overlap between the three is so very obvious that in order to understand the physical properties of sound waves, you would like to understand how they are produced, and if we know how they are produced, we understand the acoustic properties better. Similarly, if we understand the auditory impact, auditory effect it's going to have on the hearer, whether the hearer is actually going to make a distinction between certain sounds or not. So, that relating to the transmission properties, the three together constitute a comprehensive account of phonetic properties of sound waves. So, a little bit of articulatory and a little bit of auditory impact will also come into the picture as we discuss acoustic phonetics. For the present unit, since this is an introductory unit, we would like to focus on a sound wave and the most important properties of sound waves, which are time, amplitude and frequency, and then distinctions like basic distinctions like simple and complex waves, periodic and aperiodic waves, and what we perceive as musical versus non-musical sound waves. And then in the later half of this unit, we will talk about what is a spectrum and what is meant by a spectral representation of a sound wave, and then followed by the spectrographic representation of a sound wave, what is meant by a spectrogram. And then to end the unit, I would also like to mention how speech sounds are discussed in the entire scenario, because we talk about the source and filter mechanism in the production of as acoustic theory of speech production, and therefore how these units are organized, that will be the last bit of this unit. A simple sine wave, as you can see in on the screen before you, there are two pictures on the slide. One is a simple sine wave, which shows the x-axis taking care of the time, y-axis showing the amplitude or the maximum deviation or deflection from the position of rest. And then one complete cycle makes the wavelength, and the number of cycles per second is calculated as the frequency of the vibration of the sound wave. A similar kind of a representation, the real time representation, can be seen in the two pictures alongside, where again time on x-axis and amplitude on y-axis. Now, if you expand this, if you increase the expand the whole picture, zoom in, you will find similar kind of sine waves over there. So, these two are pth and puth oscillograms of Peet and Poot, two Hindi words as articulated by one male adult speaker in our JNU language labs, phonetic labs. So this is just to give you an a sound wave in the time domain. Now, in order to have a sound wave produced, there are two kinds of preconditions which are necessary for the production of a sound wave. And in case you've had some exposure to the physics of sound in your school or college before, then perhaps you would understand this, that sound cannot be, cannot exist on its own. It has to have a source or source of energy, as they say, some kind of disturbance of the air particles or whatever particles, whatever is the medium. So there has to be a source of sound, and then that energy is transmitted through a medium. The medium could be something solid, something liquid, or air. In case of sound waves, speech sounds particularly, we are focused on air as the medium of transmission. You must have heard about very simple experiments which show that there is an electric bell enclosed in a glass chamber, and then that chamber can be, all air can be taken out so that a vacuum is created around that bell. So you press the electric switch from outside and the bell rings, but the sound of the bell does not get transmitted outside that glass enclosure because there is a vacuum. Unless there are particles of air to carry that energy forward, there can be no sound waves. So these are the two preconditions of sound waves. That is number one. Secondly, in case of speech sounds, larynx is the source of sound. The vibration of the vocal cords leads to production of phonated airstream, meaning airstream coming out of the chest and airstream passing through the larynx. That gets phonated when you actually want to produce voice. So those details we will discuss later in some of the later units. But before this phonated airstream comes out of your oral chamber, it also gets modified in a number of ways in the oropharyngeal chamber through which it passes. So the entire theory of speech production, it somewhere started in 1848 by Mueller's source filter theory of speech production. This is an acoustic theory of speech production. In articulatory terms, you talk about airstream mechanism, phonation process, oronasal process, and articulatory process. 4 processes together contribute to the production of speech sounds. In acoustic terms, these are the 2 most important factors. One is larynx as the source of sound, and the supraglottal chamber, oropharyngeal chamber, through which the phonated airstream passes. That causes some kind of resonance or filter phenomenon. So source filter theory of speech production is the acoustic theory of speech production, which was of course later modified by more elaborate versions of it came into the picture. So we will talk about that in detail in later modules. Now what you see on the screen is periodic and aperiodic waves. There are 2 samples. Periodic wave, periodicity is defined as something which is happening at regular intervals. So the first one is a periodic wave which is fairly regular, perhaps the same kind of a frequency is repeated. Aperiodic, there is no such pattern. So there is one kind of wave in the initial segment, and then it changes form. So the number of cycles, the frequencies are very, very different in the different components of this different segments of this particular wave. So periodic and aperiodic waves look like this in the time domain. We move over to simple and complex waves. If there is a simple sine wave like we had depicted before, and now on the screen you see the first 3 waves. one perhaps 100 cycles per second, the second one 200 cycles per second, the third one is 300 cycles per second. So in the first wavelength that you see for the first wave, in the same cycle you see 3 cycles in the third one, which is 300 CPS. Now if such 3 waves combine together, the resultant wave can be seen in the picture at the bottom. This is a figure from Ladefoged 1962. The resultant wave, again, since the constituent waves are periodic and regular simple sine waves, so the resultant is also a periodic wave, and but the frequency of vibration of this particular resultant wave should be the highest common denominator of the 3 waves, which is 100 in this case, 100 CPS in this case. Now coming to the simple or complex waves, you know, what I have presented before you is the oscillograms. All these pictures that you have seen, the periodic, aperiodic, and earlier this oscillogram of a sound wave, they are all in the time domain, but the auditory process is such, what we hear is, we hear frequencies, the constituent frequencies of a complex wave. So what are the constituent frequencies, and how much is the, you know, in relative terms, how much is the intensity of each one of those constituent frequencies? That is the most important fact for the ear to hear these sounds. So for hearing, for the auditory purposes, you know, from the point of view of audition, auditory reception of the sound waves, it's not so important to have time on the x-axis. For us it is important to represent frequencies and their amplitudes. So we have something called a spectrum. A spectrum gives you a representation of a sound wave. For example, what you see on the screen is frequencies on the x-axis and amplitude in relative terms of all the constituent frequencies. So what you see here is a number of lines, which means a large number of frequencies are actually constituents of this particular tone, this particular complex wave which is being produced. In this case it is fairly regular, so perhaps it is the vocal cord vibration, and therefore, you know, the vocal cords vibrate at frequency x, then there are harmonics, they are whole number multiples, so a very regular pattern can be seen. So x is followed by 2x, 3x, 4x, 5x, which means whole number multiples of the first frequency. So it's a fairly regular pattern. There are certain peaks in between which shows some kind of resonance must have taken place. So these are the details we would like to know about vowel sounds, vowel production in another module. But for a spectrum, you need to have frequency on x-axis and amplitude on y-axis. Now that leaves us the third parameter. So is there a way we could include all the 3 parameters if need be, time, frequency and amplitude, and have a complete representation? For that we will need a spectrogram. What you see on the screen are 2 Hindi words, Peeth and Pooth, pronounced by a male speaker in the JNU phonetics labs. So this is a spectrographic representation where time is taken care of on the x-axis, frequencies are marked on the y-axis, and the lightness or the darkness of lines shows the intensity or the amplitude or the intensity of the sound waves. And these 2 dark bands, two columns showing dark bands of resonant frequencies, 2 columns represent those 2 vowel sounds, E and U, as pronounced in Peeth and Pooth. This particular spectrogram has a lot of noise, as you can see in the background grayish matter, spread all over. But normally in a soundproof recording room, this would not happen. So a spectrographic representation gives you the 3 parameters, and there are different uses of spectrum and a spectrogram for our phonetic representation as well as analysis purposes. We go back to the complex sound waves. We talked about periodic and aperiodic waves. Now, those periodic and aperiodic waves, they have an auditory impact which is very, very subjective kind of assessment of the sound waves. Periodic waves heard as musical sounds, meaning they appeal to the human ear, and non-periodic or aperiodic sound waves, they really do not appeal so much to the human ear. So, therefore, they are considered non-musical or noises as you call them. So, musical, the title of this slide is musical and non-musical sound waves. This is basically recapitulating what is periodic, what is regular, and generally represented by a line spectrum. A very clear, sharp peak spectrum is musical to the ear and pleasant to the ear, and something which is non-periodic and irregular and can be called a noise because it is not so pleasant to the ear. And as far as spectral representation is concerned, the line spectrum, meaning pure tone, one single line on a spectrum would mean that there is one clear frequency with no additional noises in the background or no haphazard patterns there. So, that pure tone, or a peak spectrum with just a few tones before, a few other frequencies before and after. So, peak spectrum, they definitely sound very musical, very clear and musical. But if there are dampened waves, then you find what you get is a flat spectrum where there are hardly any peaks. There are a number of waves and they come and almost in the same range, or maybe a little bit of variation is there. There are no clear peaks which are captured by the human ear, and dampened waves with flat spectra, they are generally considered not so musical to the ear which is receiving the sound wave. In fact, in later modules, we will also bring in the distinction, we will need to bring in the distinction between vowels and consonants. And Mamberg has defined, the acoustically defined the vowels and consonants as musical and non-musical respectively, musical sounds and noises. Music versus noise as the vowel and the consonant distinction, which is very interesting, how vowel sounds are, resonant sounds, and they are more, better heard, high sonority and so on. So, we will discuss each one of these properties in the later modules. So, to end this module, once again I would like to mention the acoustic theory of speech production is the source filter theory of speech production as presented by Mueller way back in 1848, whereby we take larynx as the source of sound, and the larynx and the source of sound and physical properties of voice, they are covered in module 11, which is the following module after this. And then the second major part, which is oropharyngeal chamber. Once the source of sound has produced phonated air stream, it comes into, from glottis, it comes into the oropharyngeal chamber. So, in that chamber, oropharyngeal chamber, from larynx to the lips, the entire chamber provides passage to the voice and modifies the same in a number of ways. In articulatory terms, we discussed, how the articulators move and the places and the manners of criteria are different for different kinds of speech sounds. So, all those modifications actually modify the airstream, phonated airstream in a number of ways. So that there is a filter phenomenon, meaning resonating, some sounds are resonated and the others are filtered out. So the oropharyngeal chamber acts like an acoustic filter. So the module 12 will deal with oropharyngeal chamber as the acoustic filter, module 11 on larynx as the source of sound and physical properties of voice, and then the following subsequent modules will take care of, you know, the how laryngeal tone is heard or received by the human ear, and then how the same tone is modified, producing vowels and consonants and different kinds of sounds in the subsequent modules. So we expect you to, at the end of this module, we expect you to be just familiar with what is a sound wave and what is a spectral representation of a sound wave, what is a spectrographic representation of a sound wave, what is meant by music, what is meant by noise, and periodic, aperiodic, and flat spectra, peak spectra, those basic kinds of notions which will help you understand the subsequent modules better. Thank you very much, and there are some exercises which you can, you know, follow for a recapitulation of this. Thank you very much.